Okay, everyone, please take a seat. Thanks. And welcome to the Authenticated Key Exchange session. We have, first of all, 2 talks about something related to password authenticated key exchange. And after that, the real world crypto sessions, very tightly aligned to that. And we will start with the talk password authenticated TLS via OPAQUE and post-handshake authentication. Julia will give the talk, and yeah, let's welcome Julia.
Thanks, Paul. This is joint work with Stash Jarecki, Hugo Kravczyk, and Christopher Wood. And Stash is also here if you have questions about this later. Okay, so there have been many predictions when we will finally stop using passwords. Still, the average number of accounts that are protected with a password of US or European citizens is far beyond 50. So let's have a look at what happens cryptographically if we authenticate with a password to one of these providers. So the ugly truth is that almost all password authentications work with something that is called password over TLS. You can take a wild guess how this protocol looks. I'm going to describe it. So first, you're going to establish a TLS connection to your provider. Then you verify the certificate of the provider so that it's actually the company you intend to talk to. And then you're going to send your password in the clear over this TLS connection. Okay, and then the provider hashes the password and compares it to the database of hashed passwords or somehow encoded passwords. Okay, so what is the problem with this approach? You probably know these headlines. GitHub exposed user passwords to their employees. Twitter accidentally logged the passwords while hashing them. And Facebook did a similar thing with several hundreds of millions of user passwords. So these passwords lie in the systems of these providers in the clear. And of course, none of this happens intentionally. But the systems that these providers deploy, they are so complex that it would actually be a miracle if everything works as expected. But there's a very simple way to avoid these kind of problems. So I give you a short guide to secure password authentication. First, you establish a TLS connection to the provider, because this is simply how talking on the internet works these days. And then you convince this provider of your password knowledge, but without leaking any additional information about the password. The good news is we have all the tools. We as cryptographers, we have all the tools to do secure password authentication. You can view this, for example, as an instance of a zero-knowledge proof, where you prove in zero-knowledge that you know, for example, a pre-image of a hash. You can view it as an instance of a multi-party computation, or you can view it as an instance of asymmetric password authenticated key exchange. Asymmetric password authenticated key exchange is a 2-party computation where the client on the left-hand side inputs a password into the protocol, and the server on the right-hand side inputs some form of encoded password. So most of the time I will just write hash of the password, but you can really think of any sort of encoding. Kind of makes it hard to revert to the password. Okay, so this protocol between the 2 parties takes these inputs, and as outputs, both parties are going to compute a key. Okay, and we have the guarantee that if the password data that was input matches, then these keys are going to match, right? So this is an if and only if. Okay, so because we are mainly interested in verification of the password, we have to do a bit more work here. For example, we can do a key confirmation, round of key confirmation, append this to this PAQUE protocol to let the parties learn whether the keys that they computed are actually the same. Okay? Okay, so isn't there a trivial solution to this password over TLS problem, this like way of sending passwords over TLS connections in the clear, can't you just run an APAQUE over TLS? So this would look as follows. We have the client on the left-hand side establishing a channel to some provider, and after verifying the certificate of the provider, so after establishing the channel, the client and the server run this protocol over the channel, and the outcome at the server side is essentially a bit, right? And from the security of the primitive, so from the security of the asymmetric PAQUE, the server learns nothing else, okay? So the provider does not see the clear text password. The guarantee is much better as on the slides. It actually learns nothing about the password beyond the result of the verification. And this is also because the APAQUE requires the password as input. This is somehow a proof of knowledge of the password. Okay, so this looks good already. However, there are certain drawbacks to this approach. So first, this is a proof of knowledge of the password, but the question is by whom? Because, so this is the person who is actually talking on the channel, kind of the end point of the channel, but if there's simply APAQUE messages coming out of the channel, this person can just relay these messages kind of maliciously, sneak them to another party. This party might think it's doing something else, but actually runs like this, proof of knowledge of password for that party. Okay, so there seems to be like an improper binding between this authentication action and the channel. And the other downside is efficiency. So I told you before, it might have looked already a bit weird. We are exchanging a key, and then from that key, we are again deriving a bit. So is it actually necessary to exchange this key? Can we somehow derive this bit like more efficiently, or do we have to go via this key? There's a better protocol that we can use, and this is called TLS-OPAQUE. This is an IETF draft, and it offers so-called post-handshake password authentication. So what does this mean? Post-handshake really means after establishment of the channel, okay? So you see here, well, a picture of a TLS channel. What do the parties know about each other? Well, the user has verified the server certificate, so the user knows who is talking to. The server knows nothing about the client, right? There's an option, it's optional on TLS connections to also verify a client certificate, but it's not really used at all. Because clients usually do not have certificates. Okay, so what does TLS-OPAQUE do? In the client-server setting, where we have a server storing something like a password file, a database of password hashes, for example, TLS-OPAQUE allows, after establishment of the channel, to add password authentication to this channel. Okay, so here in this example, Bob has the password. They can just, press a button. After using the channel already for some time, they can press a button, activate this like TLS-OPAQUE protocol, or run this TLS-OPAQUE protocol, and the result is that Bob is convinced that the other endpoint of the channel, this guy here, knows the password, right? So he's then convinced, okay, I'm talking to a person who knows the pre-image of the hash, so I'm talking to Bob, okay? Okay, and all of this is done in a zero-knowledge way, meaning that the server learns nothing else. So in this work, I'm going to show you a modular analysis of the TLS-OPAQUE protocol. The basis where we start from, or where TLS-OPAQUE starts from, is the channel. So I told you it's post-handshake authentication. We have to assume that the channel is already there. So this is the empty channel, the empty TLS channel that I already showed you. And a property of the TLS handshake is that both parties have like a joint secret knowledge. This is called the TLS master secret, MS. And this is essentially what qualifies them as endpoints of the channel, the knowledge of this master secret. The record, so the actual encryption keys are derived from this master secret. And what we would like to do is that we would like to bind the authentication that these parties perform to the knowledge of this master secret. Okay? And for this, we can derive, we shouldn't use the master secret itself, but we can derive from it something that's called a channel binder. You can, for simplicity, just think about this as hash of the master secret. Okay, we need another building block, which is a TLS 1.3 extension called exported authenticators. Exported authenticators offer post-handshake public key authentication. Okay? So you should be familiar with some of these words. Post-handshake I already explained, but now there's no password here, there's a public key. Okay? So this exported authenticators protocol allows TLS endpoints to authenticate under public keys to each other after establishment of the channel as often as they want in both directions. Okay, so this is an RFC. You can find it here, also an IETF RFC. Okay, how does this work? It's very simple. It's essentially sign and MAC. In this case, I'm going to show you a client who wants to authenticate to a server. Okay, so the client holds a key pair. Then he derives a MAC key K from the channel binder in a deterministic way. Just, again, think about this as hashing the channel binder together with some label. Okay? And then he's going to sign the nonce and the channel binder, actually a hash. Sorry, not the most recent version of my slides. A hash of the channel binder and the nonce. And then he computes a MAC on this signature, on the channel binder and the nonce, I believe also on the hash of all these values. Okay, and then he sends the signature and the MAC and the public key to the server. The server can derive the same MAC key because he knows the same channel binder, because he's an endpoint of the very same channel. And then he can verify the signature under the public key that was sent, and he can verify the MAC. And this is essentially a proof of knowledge of the secret key belonging to the public key of the other channel endpoint. So if this verification passes, the server kind of adds to his, like, in his head, okay, I'm talking to somebody who knows the secret key to the public key here, PK. Okay, I want to talk about password. I wanted to show you like secure password authentication. Why the hell am I talking about public keys? The reason is that we have a simple tool going from passwords to public keys. This is called OPAQUE. It's actually an asymmetric password authenticated key exchange protocol, but we're not using the whole thing. I told you before, I want to kind of skip the key confirmation part. We're not using the whole thing, we're just using a small part of it, or like, let's say not a small part, but a part of it. It's a password-based protocol, so the first thing in a client-server setting, we need to establish some sort of knowledge about the password at the server, which is called a password file. Okay? So this is called registration. Both the client and the server, they generate a key pair, and the server additionally generates a PRF key. Okay? And then they both engage in a two-party protocol, which is called an oblivious pseudorandom function. It's an oblivious evaluation of a PRF, of which the server contributes the key, the PRF key, and the client contributes the input on which the PRF should be computed. And the client also receives the output. Okay? And this is essentially a secure computation, meaning that the server learns absolutely nothing, and the client also learns nothing about the key K, except for this one PRF value. So the client has now somehow hardened or transformed his password into something more secure, roughly, intuitively. And now, so this is called the RW value in the OPAQUE specification, and he's going to use this RW, this kind of hardened password, as an encryption key to encrypt his own secret key. Okay? And he's also encrypting the public key of the server along. So this is called the opaque envelope. And now the client is sending his name, just some username that he chooses, the envelope, and his own public key to the server. Okay? And the server stores this all under Bob's password file. Okay? Okay, now in the online phase, when we actually want to retrieve these public keys again from the password, it looks very similar. So the client comes, says, hi, I'm Bob. The server can retrieve the password file for Bob, and he finds again this like PRF key, here the same that he used before, and then they're just going to do the same as before. They're going to recompute, the client is recomputing the PRF value of the password, and then the server sends the envelope, and the client can decrypt his secret key from the envelope. Okay? So the result of this step, of this opaque step, is that both the client and the server hold their own secret key and the public key of the other party. Okay? And from this, we can now invoke the Exported Authenticators protocol, which we can use to prove knowledge of these secret keys to each other. And this knowledge of the secret key, it corresponds to the password. So actually, it's not entirely true. It doesn't correspond to the knowledge of the password. It corresponds to either the knowledge of the password or the knowledge of the secret key. Okay? But since somehow this account is tied to this secret key, this secret key is kind of somehow superior knowledge of the password, so we're okay with somebody who just remembers the secret key instead of the password. Okay, so this is device independent. Bob doesn't have to remember his secret key. He can lose all the data and use another device and just start from the password. And also crucially, the password only was involved in the last 2 slides, and the server never saw the password, which is what we wanted to achieve in the first place. Okay, so putting things together, on the first layer we had the channel establishment, which is the TLS handshake in this case. We saw that we can have public key authentication on this channel, tied to this channel actually. And then we saw that we can actually retrieve these public keys to authenticate with from a password. Okay? So this is, as I said, called the TLS-OPAQUE protocol, and it gives us post-handshake oblivious password authentication that we can just switch on a TLS connection. Okay, so to analyze the security of this rather complex protocol, a modular analysis is kind of in place because it has all these modular components already. So what we did is we abstracted the channel to the TLS handshake to an unauthenticated secure channel with a unique binder. The next level is that the Exported Authenticators protocol gives us something that we call post-handshake public key authentication. Okay? And the third layer, we actually don't abstract it anymore because it's just a specific protocol, this specific part of the OPAQUE protocol. Okay, so to prove the security of TLS-OPAQUE, first we have to formalize these building blocks, and we also, of course, have to formalize what we want to achieve in the end. So what is actually post-handshake oblivious password authentication? And then for the proof, we completely ignore the left-hand side of the slide, the blue box and the actual TLS-OPAQUE protocol, and you just look at the right-hand side of the protocol, where you have these abstract building blocks that are much easier to deal with than protocol transcripts and messages and so on and so forth, and actual instantiations and groups. Okay, and then we prove that these abstract building blocks give you this post-handshake oblivious password authentication. And then essentially to derive the security of the TLS-OPAQUE protocol, we just have to prove that the building blocks instantiate these abstract, that TLS handshake and the exported authenticators instantiate these abstract building blocks. Okay, so then after proving these 3 things here, we get the final result for free. So what is the benefit of such a proof? It makes things easier for the prover. You can write 3 proofs instead of 1 big one. And the other benefit is actually the lifetime of the proof. So it's a fairly modular protocol. It uses these many building blocks. And I told you, so currently it's built up on TLS. It uses this EA extension. It actually deploys a Diffie-Hellman-based OPRF. But at some point, maybe you want to run this on another channel, or you finally manage to find an efficient post-quantum OPRF. Unfortunately, there's none in the program. And these modular building blocks that we defined, they kind of give you the properties that these future building blocks needs to fulfill, such that if you replace them in the protocol, the overall security proof is preserved. Okay? And this is something that we really need to worry about these days, that not only our protocols are post-quantum, we have many things that are not post-quantum yet, and we are writing proofs for them that should kind of adopt to the setting when we find alternatives for these building blocks. I think I'm out of time. So, okay, to summarize, we proved the security of the Exported Authenticators protocol. We proved the security of the TLS-OPAQUE protocol, and this, to our knowledge, is the first formal analysis and security modeling of a replacement of password over TLS, which, in my opinion, is something that we should really take on. Thank you.
If you have questions, please come to the front to the microphone. Yes.
Thanks for the nice presentation. What about key rotation? So TLS usually comes with something like forward secrecy, post-compromise security. Have you thought about this?
We haven't thought about this. The authentication is something rather short-term, I would say. So I would say if you rotate the key, in that case.
So you sample the secret key new fresh at each authentication, is correct? Because if you have a long-term secret key, then...
I mean, so the result of running the TLS-OPAQUE protocol is essentially a bit at the server. So if the server is convinced now, so I'm the server, I'm convinced now that you know your password, just because we switch our underlying TLS keys, it doesn't mean you forgot your password, right?
Yes.
I mean, so I can still believe that you know the password. So you kind of remain authenticated in my head, I would say.
Mm-hmm. Okay.
But it's a good point. I have not thought about how key rotation should be handled. I guess it would be that the authentication essentially remains through the lifetime of the channel. So that would be the lifetime of the channel.
Mm-hmm. Thanks.
Okay, maybe one very, very quick question. And in the meantime, the speaker of the second talk can come to the front, please. Thank you. Okay, perfect.
Okay, a short question about the point 4 here, strong password protection. Is that also guaranteed when, server, for example, the server is compromised of the K, which is used in an OPIF? Would you mind going back to the retrieval slide? And here, if the key is compromised and if the password does not have enough entropy, if I know the key as well as the, let's say, the envelope here, is it possible to recover the password? Or?
Yes, so if the key is compromised, and so, I mean, the key is stored here in this password file. So we would assume that if the key is compromised, the envelope is compromised as well. And this would allow the attacker to run offline dictionary attacks against the password file. You can essentially think about the key. The key is essentially just, this is a hash function, a keyed hash function. If you have the key, you can compute the hash function. So this provides no additional protection over a hashed database that gets compromised at the point of compromise, obviously. Right?
Thank you very much.
Okay, let's thank Julia again, and in the meantime, we set up the second talk. Okay, and the second talk, while setting up, should I probably help you? The second talk is titled Randomized Half-Ideal Cipher on Groups with Applications to UC, APAQUE. And the speaker is Stanislav Jarecki. Let's welcome Stanislav.
Thank you. Thank you so much. Good afternoon. Thank you for the introduction. Okay. So in this paper, we introduce the notion of half-ideal cipher in particular for group domains, which includes bit strings, just as a clarification. And half-ideal cipher is a weakening of an ideal cipher model in two ways. First, you need padding. So when you encrypt a group element, you need some extra order of security parameter bits. And also, the second weakening is when adversary encrypts, the cipher is not random. Only this m bits of cipher are random. Nevertheless, we argued that half-ideal cipher can replace ideal cipher in many password-based protocols in PAQUEs and APAQUEs. And we showed that this can be efficiently realized using a single arrow hash onto a group. So in the talk, I will explain first why ideal cipher is useful for these PAQUE applications, why implementing ideal cipher on groups was not so easy, and then have this idea half ideal cipher works, and what is the model, and why it suffices. Okay, so first, a beautiful protocol by Belov and Merritt, Encrypted Key Exchange, and in 2000, Bellare, Pointevall, and Roggeway showed that if the encryption is an ideal cipher, then this is a password authenticated key exchange. So how does it work? You have a key exchange, for example, the Diffie-Hellman key exchange. So that's the blue stuff. Alice creates G to the A, Bob G to the B, they exchange and compute their joint key. But you add a layer of password encryption. So Alice doesn't send G to the A in the clear, she encrypts it under the password. Bob decrypts under his. He encrypts his contribution. Alice decrypts that. So it's like a layer on top of the key exchange, right? And why intuitively this gives a PAQUE? Because, so recall an ideal cipher is this box in the sky that if whoever gives a password, so we call keys passwords because all these applications will use a password as a key. So you give a password and a message, and this box in the sky gives you a random ciphertext. In the opposite direction, you give a password and a ciphertext, and the box in the sky gives you a random plain text. So why this would be great? Well, first of all, it's collision resilient. So if you are hoping to create a single ciphertext which encrypts two different messages that you know what messages you want to encrypt under two different passwords, and you're hoping to create collision, you can't. Right? Because every time it's random. So therefore, each ciphertext commits to one password that was possibly used in a forward direction. So any message here is like a commitment to the password, which should happen in a password authentication. Another thing is that when you decrypt, you get random values. What does this mean? In a reduction, a decryption of any cipher under any password except the one that was used in a forward direction means it's a random challenge of the key exchange. And therefore, based on security of key exchange, you cannot break. Okay. We had a similar version of EKE that was actually an asymmetric PAQUE, client-server PAQUE. The only thing here maybe is that it's very similar to EKE. And it actually becomes asymmetric key exchange, so a client-server type. And it also uses ideal cipher roughly in the same way. Okay, so how would you implement ideal cipher? So maybe because it's such a beautiful protocol, this encrypted key exchange. It's so simple, but it wasn't used. And I think that it wasn't used. There's probably two reasons. Maybe nobody wanted to use PAQUEs to begin with at all. But even if they did, apparently EKE was patented. But another reason, I think, is that actually it's not so easy to implement this ideal cipher. So the first idea, so how about you do AES encryption of group elements? Well, that's completely not good because that's item one. Because if I give you an AES encryption of a group element under a password, then you AES decrypt under different password candidates, and you test whether decryptions are group elements. And you immediately reject different password candidates. You learn a lot of bits of password every time I use this thing. And like a few times I use it, you get the whole password extracted. Black Rockaway gave another construction like this. If the group is sort of a significant fraction of a bit string domain, then what you could do, to encrypt a group element, you use a cipher over the bit string domain in a cycle until you hit a group element. So that's an ideal cipher if the bit string cipher is ideal. But the length of these cycles will give you information about what password was used. Because if I decrypt something on one password, it gives me just one hop, but under a different password, it gives me 10 hops. And by timing, if I could see the timing information, then I will get password. So that doesn't sound like a great implementation in this domain. More recently, there were encodings using quasi-bijective encodings of group elements, invertible encodings. So You take a group element like elliptic curve point, encode it as a bit string, and use ideal cipher over bit strings. Problem solved, except that these encodings had issues. So alligator is, first of all, it works only for some elliptic curves, not for others, but also it only works for half the domain. So every other point you can do. So what does it mean? You suddenly have to resample so that your point is in the domain that the alligator actually can process. You can do, but it's not the most convenient, and it increases the running time of the protocol. Tibushi gave another encoding which is expanding and on constant time. It's a little more expensive, but I think there is less implementation, so maybe this can be improved also. Also, you can do Feistel. So 8 rounds of Feistel gives you an ideal cipher. And if one of the wire holds group elements and you replace XORs with group operations, then this is an ideal cipher too. But because 8 rounds is minimal, then you need 4 rounds on hashing onto a curve. McCoy, Rosulek, and Roy showed that a 2-round Feistel has sort of sufficient randomizing key committing properties for EKE security. Well, they showed, but not, in my view, not exactly. So one has to recheck, I think. At some point, perhaps a proof of this will be in the public domain. But there is problems in that they only managed to model this as using game-based properties. The properties didn't include non-malleability and a kind of man-in-the-middle security. And they were game-based, so I would argue they were hard to use. So our observation is that you make a small modification to Feistel and you get this half-ideal cipher abstraction, which we believe is easier to use. Okay. So how? Here is 2 Feistel, and you can think of it as a cipher on an extended domain. You have group element on one wire, and bit string on the other, hash onto a group operation, hash onto bit string, XOR. Okay. And here's the modified construction. It's the same, except you replace the XOR by an encryption. It's a bit string encryption. So on that wire, you're dealing with bits, so you can use a standard encryption. Okay, and therefore an ideal, but we require in the model an ideal cipher. The construction on the right has all these sort of efficiency benefits because in applications, it's the hash onto the group that has dominant cost. And you do the same hash exactly. As we will argue, this model of ours, which is a weakening of ideal cipher, still has collision resilience, non-malleability, all these properties of the ideal cipher that we need. Why half? It is because only the S part of the ciphertext is truly random. The T part can be, in some sense, structured. So there's just not enough happening on the right wire. But that is in the kind of password encryption applications seem basically not a problem. So it's not a problem that ciphertext, adversarially created ciphertexts, can have structured half. Okay, so we'll argue. So I will show you what is this half-ideal cipher exactly. First, let me just recall ideal cipher quickly on this extended domain now, right? So in this case, because the domain is bit string, comma, group element, so this is the plaintext format, and the ciphertext is random. And also, when I decrypt, the plain text is in the same extended domain and it's chosen at random. So that would happen if this was an ideal cipher. And what is a half? It's this. It's the red addition. So when accessing half-ideal cipher, adversary can specify what the T part of the ciphertext is, and only the S part of the ciphertext is chosen at random. And I would argue that it has basically, if n is large enough, right, twice the security parameters, then it's also collision resilient. And it has the same non-malleable straight line ciphertext to plaintext extraction, commitment, and the reduction can embed random challenges into decryptions, right? So it has all these nice properties of IC, except for this one that I don't see an application for which that would be an issue. Quickly, why, so how do we argue that this thing on the right realizes the thing on the left, right? We write a simulator that given seeing adversarial accesses to H, H prime, and IC, the building blocks of this construction, basically uses an ideal cipher in the sky and can program outputs of H, H prime, and IC in such a way that the view on the right is indistinguishable from the view on the left. Right? And this little IC box is the key, because basically the reduction, the simulator watches IC queries. And you can see that if it sees an encryption query to the IC box, then it sees R and K. And from K, by collision resistance of H prime, it gets password and T. And now from R and T, it gets M. So it asks the orange box in the sky, but it knows T, so it pushes the T. Okay, what's the S? And it programs S into the output of IC. And the decryption is also possible. So, but still, we need the blocks, the bit size stuff on the left to be twice the security parameter, because everything is the collisions. Create a explicit distinguisher. Okay, so so in practice we have to start with an IC ideal cipher that has 256 block size and key size. Just a little note that in the proceedings we have other interfaces. What I told you was the adversarial interfaces. There is also honest party interface, which does not expose randomness to the environment, essentially. Excuse me, and it's not clear that it's needed. Perhaps it's actually even, confusing to have this as an additional interface. I'm not sure. Okay, so very briefly, I want to say that even though this works, we did have a bug in the conference version of the paper. And I can tell you what that is. So in actually two bugs, as far as I can tell, counting. So here is the theorem set that actually this thing on the left compiles passive key exchange to PAQUE. That doesn't seem true, and thanks to Manuel Barbosa, Kai Kellert, Julia Hesse, to whom we are doing some follow-up work, we sort of realized this is not true. So why? Here is maybe subtle, I don't know. Take an adversary who knows the password. Okay, so this actually kind of removes all the password encryption layer. It's irrelevant. He knows the password. There's two people, Alice and Bob, who have the same password. Adversary knows it as well. So therefore, all this password encryption you can throw out. And what's underneath is just the basic key exchange, which is not actively secure. if the key exchange is only passively secure. So, right, so attacker knows the password. He sends Bob's message to Alice. So she computes Diffie-Hellman on AB, but he gives his own contribution A star to Bob. So Bob computes the key on A star B. And now if, for example, A star is A square, then one key is the square of the other, you know, if you use plain Diffie-Hellman, right? So it's like rather glaring. And so that's a, you know, it's an attacker who, it's an active attack. So how come, you know, okay, it's an active attack, so what's the issue? The issue is that it's an active attack on only Bob. Alice was connected passively, so she should be secure, and she's not. Given Bob's key, attacker sees Alice's key. So what's the fix? This needs to be a one-time actively secure key exchange, and a hash Diffie-Hellman is. Okay, so this is maybe why also the beloved point of the Rogoway actually don't have the generic compiler for any key exchange, but a specific one, and in fact they're using hash DH in the 2000 paper.
Maybe you have to wrap up. Sure.
Okay. Yeah, there is one more subtle thing that, okay, so you can look at the slides. Maybe one thing I should say is that recently on ePrint there is, we also do a version of this for using any anonymous chem that has applications to post-quantum secure chems. And Beguinot et al. Have a paper that basically have almost identical compiler. There's a differences in how the key derivation is done, and there are some questions like with you know what is necessary and sufficient in key derivation. To wrap up, so this is what we do. Some questions are like this ideal cipher that we use needs 256 bits, and I'm actually not sure how to construct it. So, like, I'm not a symmetric cipher design person, but I'm not sure that you know, are there some stuff that we can just take out of the box, and there maybe. If you really care about some application, it would be nice to actually throw away this and go back to the original two Feistel of McCoy, Rosulek, and Roy. In particular, for post-quantum security, maybe it's easier to analyze hash functions than ideal ciphers. Okay, thank you.
Okay, due to the time, maybe take the questions offline. Yeah, and we have a 7 minutes track switch break, and after this we will continue here with the Real World Crypto session. See you in 5 minutes. And let's thank Stanislav again.
Shall we do it like next time?
Yeah, you can absolutely. I didn't know that you will do it, so I just ran over.
I think it was like...
But we can.